we're living on a prayer that these log functions are going to be our friends here today. We've got our hands full. We're going to do a lot of graphing. In fact, we've kind of talked 2 lessons into this one, and I'll be sure about the halfway point. I'll tell you when to start a new fresh page in your notebook and to make a new title and so forth. But as far as our log functions go here, let's go ahead. We'll jump right in. Our basic log function says that f of x, or of course you could say y right there, equals log base b of x, okay? Now let's make sure the b is a subscript. Let's make sure it's small, below ground level. If you want to, we could put parentheses around that x. That's optional. A couple of other fun facts here. That b value that I was talking about, first of all, he has to be greater than 0. That number will always be positive. In fact, it'll never equal 1. Okay, it's going to be positive but not equal 1. That's kind of funny. But anyway, the domain of these functions, in other words, what is x allowed to be? We're going to say that x has to be a positive number. Okay, x has to be a positive number. In other words, we're saying x cannot be 0, and x is not allowed to be negative either. Now, as far as what is that equivalent to, we talked about the other day that every log function could be converted to an equivalent exponential function. We're just translating from one language to another. So when we said that y was equal to log base b of x, we could say that that is equivalent, and I like to use this double arrow to show that it's a two-way street. We could say, do you remember that Goofy, we used to go kind of around the world here, we're going to say b raised to the y power equals x. Okay, b raised to the y power equals x. And of course, we could just turn that around and say x equals b raised to the y power. But what we have here is these two expressions are equivalent to each other. Graphing this function here would produce the same image as graphing these. Now, the reason I prefer the one over here on the left is the fact that the y is by itself. You'll notice when you look over here at the exponential version, y is not by itself and makes it a little harder to graph, especially on the calculator. And then last thing I want to go over is, how do we pronounce this? I think being able to communicate within our groups is so important. We're going to say that y equals log base b of x. Okay, emphasis on, let's make sure we're using the word base. Let's make sure we're using the word of. That's the one I'm most worried about right there. All right, our first graph, we want to try to graph the function y equals, or f of x equals log base 2 of x. Okay, now, I've got to go over 2 different versions here, depending on what kind of calculator you have. If you have the TI-84 and it's updated, then I'm going to go over that one first because that's kind of exciting. This is brand new, about a year or 2 ago. If you hit the alpha button, which is a green button, and then you hit up at the very top row, the window button, which is F2, okay, you're going to get a menu that looks like this. And we're going to go all the way down to choice 5. That's the one we're really excited about. And if you hit that choice 5, it's going to give you something like, I'm already in my y equals menu, but you'll end up with something like this, where you're allowed to type in the subscript 2 and then use your right arrow to go type in the x. Okay, so that's if you have the updated version. We hit alpha, then we hit F2, and then we chose choice 5, and we're able to type in the subscript and the x. Now, if you don't have the updated version, okay, for instance, if you have a TI-83, then updating it's not even an option. We got to get a little more creative. We have to go back and we have to remind ourselves of this property or this theorem called the change of base rule. Okay, and what we're going to do is the change of base rule says that log base 2 of x is equivalent to log base 10 of x divided by log base 10 of 2, which the base 10 can be invisible, and we could just say log of x divided by the log of 2, and now the calculator can handle that. Okay, and so if you have the 83 version, you're going to go ahead and you're going to type it in just like this in this little image I show. So you've got log of x, make sure you close that parenthesis, and then you got your divided by, and then you got the log of 2, and it kind of ran out of my screen, but you'll be able to figure that out, I'm sure. So regardless of how you typed it in, whether you went with the updated version over here or you went with the non-updated version, hopefully your table of values looks similar to what I've got right here. Now, perhaps the most exciting thing is what's going on here when x equals 0. The calculator is saying that my y value is an error, which means there is now an asymptote. So it's a little easier to spot the asymptotes for the log functions because the calculator literally says error. The first time you see the error is where that vertical asymptote is going to be. Whoops, I just goofed up here. See if we can erase this at all. That didn't do it. Let's see. Hopefully that disappeared. Okay, now, so the first thing that I'm going to do, and we're going to do this with a nice bold pen here, is I'm going to put a vertical asymptote right there on top of the y-axis when the x value equals 0. So the first thing I graph every time on my log functions is that asymptote. And then after that, we can talk about graphing the rest of these points. Well, we've got 1, 0. Let's see. We've got 2, 1, and so forth. I'm going to skip a couple. Let's try 6, 2.5. Okay. Not real tall, you'll notice. Okay. What's happening is the graph starts very, very close to that asymptote. Okay. And then it curls this way and tends to almost flatten out. It's still increasing a little bit, but at a very, very slow rate. So we're very, very close to the y-axis. The graph is approaching the y-axis down this way. Okay, now technically, within this region right here, it never touches the y-axis. We say it's asymptotic. But certainly it gets infinitely close. There's just a very little bit of daylight in between those two. One last thing I'd like to point out before we move on to our next one is that this is, I'm showing you a picture of what my calculator screen looked like. Not a picture that we're really in love with. The first thing, just like with the exponentials, the calculator does not display the asymptote, and that's what's disheartening here. So know that for sure that there is an asymptote there. It kind of appears that the graph runs right into and touches the y-axis, but it doesn't. And you'll notice that from that point on, it continues to increase, but at a very slow rate, but it's still going up a little bit. Okay, now what I want to do is I want to talk about the domain and the range and the equation of that asymptote. First things first, what's the equation of the asymptote? Okay, what's the equation of that asymptote? Well, we know that the asymptote's right on the y-axis, but what's the equation? Okay, I'm going to say that the equation is x equals 0, and that's just another way of saying the y-axis. Okay, how about domain? We're just kind of trying to squeeze these in wherever we can. The domain. We mentioned earlier that it is the set of all x's such that x is greater than 0. Okay, that's our way of saying that x is allowed to be positive. That's it. No negatives. Okay. In other words, the graph lies entirely to the right of that vertical asymptote. And as far as the range goes, you'll notice that my graph does go infinitely low and it does go infinitely high. So I'm going to say the set of all y values such that y is an element of the set of real numbers, okay? That's our mathematical way of saying that the graph extends as low as negative infinity and as high as positive infinity. The next graph I want to talk about is a very, very special graph, and it's the graph of y equals the natural log of x. Now, you'll recall from a previous lesson, natural log is so special, we created its own name just for this function. It's really log base e of x, but we never write it this way. We kind of use our shorthand notation and just say ln of x. Now, as far as heading to the calculator, remember our calculator has a very special button right here just for the natural log. So you can go ahead, go to your y equals menu, then come on down to this left column towards the bottom, hit your ln, then type in your x, close your parentheses. Hopefully your y equals menu looks just like this. And then we'll go ahead and we'll take a look at that graph. Notice the first time you see the word error, that tells you exactly where your vertical asymptote is going to be, okay? So it's similar to the last problem where we're going to have an asymptote right on top of the y-axis. And then what we'll do is we'll do the best we can to plot, 3 or 4 of those points and see what kind of pattern we get. So first things first, I always like to start off with drawing that asymptote. I want it to be very bold and pronounced and obvious, okay? I don't want to have to go hunting for it. Now what we'll do is we'll pick out a few of the friendlier points, and we know that it goes through 1, 0. Let's see, 2, oh boy, 0.69. Not the easiest one to plot. Let's see, I'm going to fast forward all the way to 6, 1.7-ish. just below the 2 there. We know that it's going to start very close to the y-axis, curl up and through those points there, almost flatten out, kind of plateau-like, but not quite. So you'll notice, even though it's a different function, it's extremely similar to the last one we did. If they wanted me to write the equation of that asymptote, I would simply say x equals 0. If they wanted to know the domain, I would say that it is the set of all x values such that x is greater than 0. In other words, it lies entirely to the right of that vertical asymptote. And then last thing here, if they wanted to know the range of this function, we could say that it's all y values such that y is an element of the set of real numbers because the graph extends infinitely low and then infinitely high, although be it at a very slow rate. The last graph we want to try to attempt tonight is y equals log base 3 of the quantity x plus 4. And we're going to see something real exciting here. I'd like you to hit the pause button right now. Enter this into your calculator. Again, if you have the updated version, you're going to hit alpha F2, and choice 5 will give you that real fancy version of the log. And we'll generate a nice table of values. I want you to pay especially close attention to where that new vertical asymptote is, okay? Go hunting for that new asymptote. Okay, here's the table of values I ended up generating, and you'll notice that we have a new asymptote that is moved back to -4. You'll notice on your table of values, -4 is the first time where I saw the error message, and that's where I'm going to go ahead and start. First thing I do every time is graph that vertical asymptote. Make it as straight as we possibly can, nice, bold, and pronounced. And then from there, I just kind of randomly picked some of the what I considered the friendlier points. We've got -3, 0. 2, 1.6-ish. Oh, let's see. Scratch that. Pretend that wasn't there. All right. I got to go to +2, 1.6-ish over here. Let's see. 5, 2 right there. 10, 2.4 right there. And I'm going to switch colors. Just seems to look nicer. So we're going to start as low as we possibly can. Cut through that x-intercept. Curl this way. Just like that, and we'll put the finishing touches on. Where's that? Didn't mean to do that. Where's the asymptote? I would say the equation of the asymptote is that x equals -4, and in fact, we could cheat a little bit. You'll notice you saw the +4 right up here. Whenever you see a +4, that means the graph got shifted to the left 4 units. Okay. So when the asymptote used to be at x equals 0, we went left 4 units, now it's at x equals -4. So it's just kind of a shortcut. We can cheat once in a while. The domain is going to be the set of all x values such that x is greater than the asymptote, which in this case -4. Range, you can take a wild guess. Really go out on a limb here. It's all y values such that y is an element of the set of real numbers. Again, all we're saying is that it extends infinitely low and infinitely high. Okay, we're now at our halfway point. I need you to, wherever you are in your notebook, I need you to stop where you're at, start fresh on a new clean page with this new clean title. We're going to talk about finding the inverse of a function. Specifically, I'm going to give you a log function and ask you to find his inverse, and we're going to look for some general characteristics. We're going to do this in 2 different special ways. We're going to first talk about doing it graphically, which I think is the easiest, and then algebraically is certainly, I think, now you're going to find out, I think algebraic is quicker, although it may be slightly more confusing than the graphical version, but hopefully not. So we're going to start off here. The first one I want to do is let's find the inverse of the function f of x equals log base 2 of x. Okay, so this is a function we're very familiar with. We put this in our notes just a few minutes ago. We graphed it up really nice, and that's what I want to talk about. Let's go back and let's recall the table of values we had for that function just moments ago. Okay, so I just went back to the table we had earlier and I pulled off what I thought were the 4 friendliest, most user-friendly points on the function log base 2 of x, okay? Now remember, what is the essence of any inverse, whether we're dealing with a logarithmic inverse or any other inverse? The essence is that what used to be your x values now becomes your y values. And of course, what used to be your y values now becomes your x values. So, when you're finding the inverse, all we got to do is take this table of values and we're going to flip everything around or swap them all. Okay, now I'm going to say my new x values are 0, 1, 2, and 3, because those are what used to be my y values. And then, now look at the title here. I'm putting f with a little -1 up there. That's our shorthand notation for inverse. And I'm going to say those values are what used to be my x's, the 1, 2, the 4, and the 8. And all we're going to do is we're going to graph both the orange and the blue function on the same axes and see what kind of relationship becomes evident. Okay, here's the picture that I got when I took a few moments to graph both. I started with the original, the orange one, okay, and the orange one was y equals log base 2 of x. And then, of course, now the one thing that I did not put on that orange graph that we have been is the vertical asymptote that you'd see right on the y-axis. And the reason I avoided that is to kind of cut down on the clutter so that these graphs didn't get too obnoxious. And then as far as the blue guy goes, I went ahead and I plotted the 4 points. I think there was a point right here, right here, right here, and then one more right here. And then I kind of took the liberty of extending that graph along the axes right here, noticing that if there used to be a vertical asymptote at x equals 0, there's now a horizontal asymptote at y equals 0. A couple of things. What quadrants does the blue graph live in? The blue graph is living in quadrant 1 and quadrant 2. Now compare that to the original orange one. The orange one was living in quadrant 1 and quadrant 4. Just a little brief review. Now there actually is a really, really special relationship here between these two graphs. And I'm going to see if I can do it justice. Okay, there's a very special diagonal line that runs right through the middle of your graph paper. Okay, right through here. Trying to be as careful as I can to get through there perfectly. Okay. And what's happening, and now the equation of that line is y equals x. And you'll notice if I had the ability to fold my paper right on that dotted line, then the orange graph would superimpose itself right on top of the blue graph and vice versa. Those graphs would lay perfectly on top of each other. So we say that this special graphical relationship is that f and f inverse are reflections of each other, we'll say, over the line y equals x. So that's a very special relationship that's going to really become important throughout the year. Now we're going to switch gears big time here. We're going to talk about finding the inverse algebraically. I thought that this is going to be a little quicker, snappier way of doing it. And we're going to stick with the same friendly function that we've been using all night, f of x equals log base 2 of x. And the first thing, I'm in no big hurry. All I want you to do is to rewrite it in a way that we replace the f of x with a y. Okay, no big deal there. We're just saying y equals log base 2 of x. Okay, now the second step is the key. We're going to now swap the x and y variables, and that's the essence of an inverse. Okay, we're now going to say that x is equivalent to log base 2 of y, and this truly is the inverse right here. However, what we don't like about that is the fact that the y is not by itself. So we need to try to clean this up a little bit. In other words, we need to solve for y. And in order to solve for y, we need to convert this equation. Hopefully you can kind of see where I'm going with this. We're going to convert from logarithmic form into exponential form, and that's what we spent just about an entire day practicing not too long ago. See if I can spell on the spot here. Got all this pressure on me. I don't want to spell it wrong too bad here. So anyway, what does it look like if we try to convert this into exponential form? What we're going to say is that 2 raised to the x power is equivalent or equal to y. 2 raised to the x equals y. Or you could spin it around and say that y is equal to 2 to the x. Holy smokes, what do we got here now? You'll notice we started with a log function. Okay, let's just kind of recap where we've gone here. We started with y equals log base 2 of x, and his inverse, okay, I'll put INV, is y equals 2 to the x. So if you start with a logarithmic function, the inverse will always be an exponential function. And in fact, the opposite of that is also true. If you start with an exponential and you solve and you want his inverse, you will end up with a logarithmic function when you're all done. Okay, we're going to get a little crazier here on this next example. We want to find the inverse of the function f of x equals the natural log of the quantity x plus 4. Okay, first things first. Step 1, we said all we're going to do is we're going to rewrite it so that the f of x becomes a y. Okay, nothing fancy there. Has nothing to do with the inverse yet. Now, here's where the magic comes in. We'll put the big star here. Step number 2 is by far and away the most important step by a mile. We're going to take the x and the y's and we're going to swap them. Okay, so step 2 is all about the swap. X now equals the natural log of the quantity y plus 4. Now, if you feel more comfortable, you could rewrite this as log base e, because that's all the ln is, of y plus 4. That perhaps makes you feel a little bit more comfortable going into this next step. Because step 3 says we're now going to solve for y. Okay, and in other words, we're going to convert it from logarithmic form into exponential, and we're going to say e raised to the x power equals the quantity y plus 4. E to the x equals the quantity y plus 4. One more little itty-bitty step, we'll subtract the 4 over. And technically, you could say you're done right now, but if you'd prefer, we could write it as y equals e to the x minus 4. And ladies and gentlemen, that is the inverse of the natural log of the quantity x plus 4. If I graphed those two functions, they would appear to be reflections over which line? Hopefully, you just said to yourself the line y equals x. Okay, last one of the night. We want to find the inverse of the function f of x equals 6 to the x. Now the big difference here is we are starting with an exponential function. We have been given an exponential function. Step number 1, we're just going to rewrite it so that it says y equals 6 to the x. Step number 2 is the most important one. That's where we're going to go ahead and no matter what kind of a function it is, whether it's linear, quadratic, exponential, logarithmic, no matter what kind of function it is, we got to swap those variables. And we're going to say x equals 6 raised to the y power. Okay. Step number 3 says we're now going to try to solve for y. And in this particular example, I'm in exponential form right now, so I'm going to now convert it from exponential into logarithmic form. And all we're going to do there is we're going to say, I don't know if you recall, our big point of emphasis was that logs are always equal to what used to be the exponent. So we could say that the log base 6 of x is equal to the exponent, which in this case is y. So just a quick little recap there. The 6 is your base, okay? Just like 6 was my base back here. The x is what used to be your answer, okay? And the y is what used to be your exponent, and that's how you convert from exponential into logarithmic. Okay, so we had a long one tonight. We squeezed 2 lessons into one. We got a little greedy tonight. Hope you're able to keep up, and we'll see you guys tomorrow.